Well, I'm Daniel Morán. I'm developer for the IoT chapter of FIWARE. And in this lecture, I'm going to show you how you can connect do-it-yourself hardware or the typical prototypal boards like Arduino, Raspberry, and so to a FIWARE platform. This is a little overview of what we are going to talk about. First of all, I'm going to give you a brief introduction of what we are going to do. Then I'll explain what hardware we are going to use in this lecture, and show you the small model of a smart city. That is the hardware, the sensors and actuators we are going to connect to the FIWARE platform. The rest of the lecture will consist basically on showing you the code we use to connect and to manage the model. And let's start. First of all, what is the goal of the lecture? The goal is to show you how to connect devices to the platform from the sensor to the context broker and back again. That is, we are going to show you explicit diagrams of the sensors, how to connect from the wires to the entity in the context broker that represents the data you can obtain from the sensor you have connected to those wires. In the hardware part, we choose to do the model with an Intel Edison. There are multiple options really for the hardware in this case. We could have chosen to use an Arduino or a Raspberry Pi and so on. But and at the end, all of them are basically the same thing. You are using a high level, some high level language to program your model logic, and you have the GPIO, the analogic enters, and so. And in most cases, as you will see in the Intel Edison case, even the input and output layout is the same between Arduino, Edison, and most of the clones of the Arduino model. There are a couple of features of Intel Edison I found interesting, and that's why we choose to use the Intel Edison. First of all, the compatibility with Arduino. Intel Edison inputs and outputs are 100% compatible with Arduino, so you can use Arduino shields and Arduino-specific hardware working with Intel Edison. A very important difference for me is that the language for programming Intel Edison, it's not a platform-specific language like Arduino C, but a common language like Node.js. It's JavaScript, if you don't know it. And it's not only the language, but the libraries you will have available with the language. If you have programmed with Arduino C, you would have found that it's sometimes quite difficult to find libraries for co-op, MQTT, or other IoT-related languages. But in the case of Node.js, all of those protocols usually have a library or a module that can deal with them. And the last strong point of the Intel Edison pack is that it has a good and easy to use toolkit that lets the people who don't know or who are new to the IoT introduce themselves in the IoT development with a lot of ease, without the needing of installing their own Yocto distribution or something like that. That would be a strong barrier, entry barrier for the development of IoT applications. Here you will see a model of the the things we are going to develop during this lecture. First of all, we are going to model a small smart city that you can see at my left. This smart city has a couple of actuators and a couple of sensors. It has parking sensors to detect whether there are cars parked in the parking spots or not. It has some lighting sensors to measure luminosity and start or stop the lighting of some of the buildings. And it has a small semaphore whose frequency can be changed with context commands. We want them to be changed via context commands using the context broker. This hardware, we are going to connect it to a small FIWARE Platform that will be consisting just in an IoT agent and a context broker. We are going to deploy that IoT agent and that context broker with Docker. You will see there are only 4 commands you need in order to get that small architecture up and running. But as you can see in the components documentation, it's very, very easy to add other components to the same architecture using Docker as well. Here you will find a diagram of the hardware, how the hardware is connected to the Intel Edison. You will find that the image on my right is really an Arduino Uno, but as I told you before, the Arduino and Intel Edison has the same input-output scheme, so you can use them interchangeably. An interesting thing is that really even the code of we are going to see that is in Node.js, it's basically translatable to Arduino, directly translatable to Arduino, as the sentences that are used to read and write the data from the hardware are basically the same. You can see here there are the very basic sensor we are going to use. We are going to use four LEDs to the lighting system, a small luminance resistor. I don't know exactly the term in English, and 2 IR sensors for the detection of the cars in the parking spots. And that's the smart city we are going to use. Well. I will now change to the SDK of Intel. Well, first, before changing to the SDK, I will show you how to deploy the Docker in the FIWARE architecture in Docker. Here I have the 4 commands we are going to need. In the picture of the FIWARE architecture I showed you before, I omitted 2 of the components that are needed for the FIWARE architecture. First of all, most of FIWARE components need a database to be run, and usually they use a MongoDB, a NoSQL database. That is the first component we have to deploy. There's also a dependence of the IoT agents. IoT agents usually have multiple transport protocols, not only application protocols like ultralight and lightweight M2M, but they can have several transport protocols like MQTT or HTTP. In the case of MQTT, there is a dependence in the Docker image of a MQTT broker that can leads with incoming MQTT connections. So that broker in our case is the Mosquito broker, even though we are not going to use MQTT in this specific example. But it's a requirement of the Docker image of the IoT agent. We are going then, I'm going to explain you a little bit of these other 2 commands. In this command, we are going to deploy an Orion context broker. As you can see, basically you have two additional options than in the case of MongoDB and Mosquito. That is the link the context broker needs to the MongoDB database, the MongoDB container in this case, and the port we're going to expose in the host. That is the standard port for the context broker. That is the 1026. Yeah. Excuse me? What was the proposal of the Mosquito again? The Mosquito is an MQTT broker. When you use IoT agents can use several transport protocols. If you are going to send ultralight 2.0 data, for example, you can send it via HTTP or you can send it via MQTT. The problem is that if you want to deploy an IoT agent, the Docker image needs both of the systems to be available. And in order to use MQTT, you need an MQTT broker, or in our architecture, we use an MQTT broker. So the IoT agent is connected to the MQTT broker, and the devices are connected to the same MQTT broker as well. So in this case, you need an external MQTT broker to be deployed along with the Docker image of the IoT agent for it to work. here is the last part of the building our architecture. And that is to set up the IoT agent. In this case, we are going to use the ultralight 2.0 IoT agent. And as I told you before, it has a link with the Mosquito, with the MQTT broker, and two links, one with the Orion context broker, and another one with the MongoDB database, where the information about the devices will be stored. As you can see, the Docker container of the IoT agent exposes 2 ports instead of 1, because I don't know if you attended my presentation on the first day, but IoT agents have 2 interfaces, have a southbound interface that exposes to the devices, and it has a northbound interface that exposes to the applications that are using the platform, so that they can register the devices that are going to be used in the practice. With this, you have all the components up and running and linked, so we can start using our application. In this case, whenever you will use an IoT agent, you always need to register first the devices you are going to use to send data to the IoT agent. In order to do so, there are 2 tasks that you have to accomplish. These tasks are accomplished just once for the lifetime of the device, and there is one of them that is accomplished once for the lifetime of your service. The first thing you have to do is to create a group of devices. The main reason to create a group of devices is to provide an API key the devices will use to connect to the IoT agent. This API key will help the IoT agent assign the devices to the appropriate service in the multi-tenant system it is going to send the data to. As you can see here, the only thing you have to do is to post the payload of your group of devices, indicating the API key. In this case, I don't know how many of you have used Postman sometimes. Well, okay. For those who haven't used Postman, this is just a REST client. It's a HTTP client that you can use to interact with APIs, sending simple requests. And in this case, this is going to send a post request to this URL, and this syntax with the double brackets, it's a syntax for variables in the environment variables you have in the program. This is the direction of my laptop. This is the port of the IoT. I think all of the variables should be self-explained. As I was saying, the only thing you have to do in order to create a group of devices is to define an API key and a type for all of those devices. This is the type that will be assigned to the entity in the context broker that will be created when a device is provisioned. You will have also to define the protocol the devices are using. In this case, is ultralight 2.0, and the path where it is where the data will be sent to with HTTP. We can see the status as it's 201 created. That means the group has been created all right. Next thing we have to do is to create the device, to provision the device in the IoT agent. This device will have the same entity type that we defined in the previous group, the same protocol, and the interesting information in the provisioning is there are two interesting pieces in the provision of the device. First of all, the device ID will be used by the IoT agent to determine the identity of the device, to know to which entity the information of the device has to be sent. The entity name itself, whenever it is created, can be customized using the entity name parameter, but it can also let the IoT agent create a default entity name, and it will usually by default, it will use the device ID, colon, and the entity type. The other piece of information that has to be defined in the device provisioning is the attributes, the information the device is going to send to the IoT agent. In this case, we can see, as we saw before in the diagram, an Arduino app diagram, there are basically three kinds of information the smart city will be sending to our platform, and that are the position, the occupation of both parking spots, and the luminance, the value of the luminance sensors. Once we send it, we obtain a 201 created status, so the creation was accomplished correctly. If we now go to the context broker, we can query for all the. Here we are querying for all the smart city type devices, and here we have our context response. As you can see, an entity has been created with the attributes we have defined in the provisioning of the device. Here, as you can see, when you define the attributes in the provisioning request, you define two kinds of information for each attribute. First of all, the object ID, that is the name the attribute will have in the underlying protocol, in this case, Ultralight 2.0. And secondly, the information the IoT needs to create the attribute in the entity, in the IoT platform, in the FIWARE platform. In this case, the name of the attribute and the type of the attribute. If we return to the description of the entity, we will see that we have the defined attributes with the default value that it's a blank space. Okay. If we go we change to the IDE to see how this is programmed in the device, we'll find mainly two concerns in the programming logic of the devices. First of all is how to read the values from the devices. In this case, we are going to use a library provided by Intel that's called MRIA. This library is a Node.js library that lets the Node.js application reads the I/O, both asynchronous I/O and asynchronous analogic and digital I/O of the device, and read and write the different I/O entries of the device. As you can see, the only thing you have to do in order to read and write the data is to define the data in a new variable called GPO in the case of the digital entries and AIO in the case of the analogic ones, and define the direction of the interaction in the case of the digital directions. As you can either put the values or you can either write the values in the board pins or read from them. In this case, all of our MRIA. MRAA. This is one. Is this one? You can see it's in GitHub. I think if you do this, you will find it very quickly. Is this one? Okay. If you are using Intel XDK, there are example projects that automatically import the library, and you will find it in the Intel Edison documentation. There are plenty of references to this library. Okay. The only thing we have to do to initialize this library is to change the input status, the input direction. That's not needed in the case of the analogical entries, because all of the analogical entries are input only. And once we have the directions, the only thing we have to do is to read in the case of the sensors, or write in the case of the actuators, the LEDs in this case. The rest of the we try to encapsulate all the smart city, all the hardware hardware management sentences inside of this module. And as you can see, the basic logic is very, very simple. We have a blinking in the semaphore. We have some conditionals to check whether we have to activate the lighting or not. And the interesting thing is we have some get and set functions we can use to retrieve information from the smart city or to set information to the smart city. Those functions will be used in the communications model that we will be using to connect the smart city we have developed to the platform we have just deployed. In the case of the communications module, the main thing, well, first of all, let me rewind a little bit. I don't know how many of you have ever used an Arduino board or some IoT board in like this one, or the Edison or something like that. Usually the program you have in an Arduino board, it's executed in Arduino or in this case, it's executed from top to bottom. So you have to define a special function, a loop, that it's going to be executed once and again, and an int function. In the case of Arduino, I think I can recall there are especially defined functions in the language to do that looping. But here, in the case of Edison, you are going to execute a script of Node.js, so there is no looping by default in the execution. But that's very, very easy to achieve in JavaScript. You just have to set a time interval with the delay you want between loops, and define a function loop that will be executed each time that time interval expires. This is what our main function is going to achieve. And in the loop of the main function, we are always going to do two things. That is to step each one of our models. A step means that it will, in the case of the smart city, it will read the sensors and write the actuators. And in the case of the communications, it will decide whether it has to send information to FIWARE, or it will have to wait and when there are commands to process, how to process them. These communications, whenever a step in the communication is achieved, what we are going to do is read all of the information of the smart city and send it to FIWARE using this send data command. This send data command, the only thing it has to do is to send a simple HTTP request. We are going to use ultralight 2.0 requests to send the information. Here it's very difficult to see here exactly how the request itself look like. How does it look like? So I have here a postman command that can give you a hint of what we are going to send. This request is cooked from the same smart city, and as you can see, the only thing we have to do is to post a text plain payload indicating the attributes we want to modify and the values we want to give to them. If we send this, we will see that we obtained a 200K status code indicating that the measure has arrived to the IoT agent and it has processed without any error. And if we get the device information from the context broker again, we will see, you will see that we have the values we have sent from the requests. In this case, there is another piece of data that is interesting to highlight. That is the metadata that have been introduced by the IoT agent in all of the attributes of the device entity. Whenever a measure arrives to the IoT agent always generates a timestamp for that measure. That is the instant where the measure was processed by the IoT agent. And that time instant is added to the description of each of the attributes, so it ends up in the device entity. The IoT agent also generates a time instant for the whole entity that has the meaning of when the entity was updated for the last time. There are also options in the IoT agents and on all of the protocols to send a particular time instant along with the measure. So the IoT agent, instead of generating a timestamp that reflects the time when the measure was processed by the IoT agent, it would generate it would write the instant where the device took that measure in the past. So a device can be sleeping and waking up from time to time, can be storing measures with different timestamps, and then send all of those measures with different timestamps, and that will appear in the IoT agent with the timestamps where they were taken instead of the timestamp where the measure arrived to the platform. And so that is for data send. And another thing we want to do with our IoT platform is to retrieve information from to send information from the platform to the device. In order to do so, we have to define commands in the device provisioning. We can update our current device provisioning, adding just the information we want to add. In this case, we want to change the semaphore frequency and the luminosity limit that it's used to decide whether the lightings of the buildings should be up or should be down. As the northbound APIs of the IoT system most likely a REST API, you only have to do a put request over the device ID you want to modify in order to add information to the provisioning of that device. We are going to send this to modify the device. We have it modified correctly. And if we get the device information, not the device information in the context broker, but the device information in, yes, okay, here. The device information stored in the IoT agent, we will see the device provisioning we had before with the device ID and the entity name and entity type. And we also have our newly defined commands. If we return to the device information in the context broker, we will see that the IoT agent has created some special attributes for the commands. For each one of the commands, in this case, for example, the luminosity limit, the IoT agent will create two special attributes. That is the command name info that will store the result of the execution of the command in the case the command is retrieving some information or an error status, for example. And the status, that is how is the status of the last command sent to the device. In this case, we haven't sent any command to the device, so the status, so the current status is unknown. Well, and let's start the application in the Intel Edison, and let's see how this is working. In this case, we are going to send a command in a moment, and the command will arrive to the IoT agent to the device in the same, more or less the same format as the ultralight data that was sent before, and it will be sent. We are going to be using poll type commands. IoT Agent offers two types of commands, that is push and pull. And in the case of the push commands require the device to be listening in an HTTP connection, so the platform can contact the device whenever it wants to send information to the device. In the case of pull commands, it works the opposite way. The IoT agents will store the commands created in the platform, and it will store them until the device itself sends any information, any request, indicating that it wants to retrieve the pending commands. We are going to send a command now, and you will see what I'm talking about. Sending a command to the device is as simple as updating the command attribute in the context broker, as you can see here. Here we will just a side note. We are going to use we are using NGSI version 1 instead of version 2 along this lecture, as the IoT agents have not still migrated to NGSI version 2, excuse me. So that's why you will find the version 1 commands in this case. Here you have the command we will be using to update some information in our device. As you can see, we are going to establish a very low semaphore frequency and a high luminosity limit in order to make the lighting be permanent instead of dependent on the current luminosity. Once the command have been sent, you can get the device information in the context broker. And you can see, well, in this case, the command status is already okay. That means it has been already processed by the device. If we see the log of the device here, you will be seeing that the device is usually sending this information. This is an ultralight 2.0 payload. And in a certain point, the device sends information, but also queries for the existence of commands that find this command. This command, once parsed and analyzed, means for the device that it has to change these two values, that is the semaphore frequency and the luminosity limit. In this case, you should be seeing the semaphore blinking in a higher frequency. How to parse this? Well, in this communications mode, you will find how to parse the ultralight 2.0 protocol, and that's it. And I think, well, with this, I think the demo itself is ending. And I don't know if you have any questions. I think I prefer this to be a little debate. Do you have questions, or you want to see specific parts of the code? Yeah. Yeah. Well, that's the question of the security from the device to the platform. It's highly dependent on the protocol you are using. For example, in MQTT, that's clearly solved. If you use MQTT instead of HTTP, MQTT brokers usually have means of authenticating the device either by client certificates or by password and user password authentication. In the particular case of HTTP, ultralight 2.0 HTTP. Here we don't have any security measures in place, and you should rely in VPNs or something like that, mechanisms based on network security. Any other question? No, all of that is done behind the curtains by the IoT agent. The only things you have to do to do this process are those that I have showed you in this demo. The FIWARE architecture was completely empty. It didn't exist before I started creating Docker containers. So that's everything you have to do in order to connect an application that uses NGSI to plain hardware, to plain hardware. Excuse me? Yeah? The IoT makes those subscriptions. Yeah, it defines itself as a context provider in the context broker. Yep. Are you using Wi-Fi? No. I wanted to use Wi-Fi, but I found some problems to get my laptop and the smart city to see themselves, so I'm using Ethernet over USB. Well, in principle, there are no variations at all. Whenever you have an HTTP socket available, the underlying physical transport it's not important, really. You can have Ethernet, Bluetooth, wireless, whatever. Any other question? Questions, comments? Yeah. Wait for the mic, please.
Are you gonna make the code available?
I think I can hear you better without the mic. Can you turn the volume of the mic up? No, I'm speaking with control. ¿Podéis subir el volumen del micro?
Sorry, I'm just asking if you're going to make the code available for that you use to program Intel Edison.
All of the code. Well, let me return to the presentation because I have a couple of links here. You may want to see. Here you have the workshop. All the code of the workshop is in the link. You can find that in Smartsville in my personal account, and we are going to release an article with all of this explained, carefully explained in the text. I'm not a good explainer, a good speaker, so maybe you find it better to read it in a step-by-step guide.
Thank you.
Any other questions? Well, so we can finish here. Thank you.